Alright, for this video, I will discuss how to integrate using partial fraction. No? So using partial fraction, or in general, using rational fractions. No? So what should we do here is, when presented with an integrand, so when you have a function in your integration that is a rational functions or a rational function, there are different ways to simplify this. So you can either use, actually the first that I will introduce is integration by partial fraction. The second one is using long division. Okay. And the third one is rational substitution. So usually the problems are in partial fraction, but I will also have an example of long division and rational substitution. So for this example, let's say you have this problem. You can rewrite this problem into this form. So why do you need to rewrite this? Well, because you cannot integrate this directly. That is the reason. You don't have a formula that integrates this directly. You cannot use substitution. You may try using integration by parts. But actually, integration by partial fraction is usually simpler for me. So you can decompose that into two simpler fractions, which is this and this. And as you can see, this is actually integratable already. It might not be too obvious, but this is integratable using natural law. So this is ln, or negative 1/2 ln of x plus 1, and this is 1/2 ln of x minus 1. So if you simplify this, we integrate this, we have ln of x plus 1, and then plus 1/2 ln of x minus 1. Okay? So the process of this, the process will be explained in the next slides. Okay? So for the different cases, no? So there are different cases actually that that can be treated differently, no? Depending on the case. So before we actually discuss how do we, or what are the process in integration by partial fractions, we have to remember that partial fraction is only applicable when the denominator is of higher degree. So let's say you have a numerator of some function p of x. You have a function below, which is, let's say, for example, this is just q of x. So for integration by partial fraction to be solvable, this should be, or the denominator should have a higher degree. Now, alternatively or conversely, if the degree of the denominator and the numerator is equal, you have to use long division. And also, if the numerator is of higher degree, you have to use long division. Again, this is only applicable when the denominator has a higher degree. So what do you mean by a higher degree? So usually we're talking about polynomials. The higher degree polynomial or the higher exponent polynomial should be at the denominator. Okay, so let's begin with the first one. So the linear and distinct. So if we have linear and distinct, what does that mean? So if we have a denominator that are linear and distinct, what does that mean? So that means that it has an exponent of 1, your excess, and it is distinct, meaning there is no repetition between your factors. So we will discuss later what I mean by that. So basically, if you have this form, then you can decompose, or what do you call this? Well, decompose na lang, no? So you can decompose this into this form so that you can integrate this, no? And you can integrate this. And then if you have this form, so if you have this linear and repeated, so basically if you have an exponent and then you have this linear factor, then what you can do here is you have to consider ax plus b and ax plus b squared. Later I will explain this during the example. There should be a plus here, no? We got the plus. And then for quadratic and distinct, so sometimes your quadratic function cannot be, or it is not factorable. There are cases where it is not factorable. it has something to do with its determinants, no? So we have b squared minus 4ac. Just double check if this is greater or less than 0. So just check if that is 2. I think if this is less than, no, less than 0, then this will be not factorable. Okay? And then quadratic and repeated. So if you have a quadratic and then repeated, so similar with linear to linear distinct to linear repeated, the same goes with quadratic distinct and quadratic repeated process. If you have here an exponent k, you have to repeat that, no? So assuming that k is an integer, positive integer, so this will be raised to 1, raised to 2, and so on. Okay? So that's it. So I'll just show you the example so that you will have a great idea what I am talking about. Okay. So for this first example, let's say you have this rational function. So the first thing that you should know, first thing you should do is you have to first analyze if your numerator and denominator, or which of the two, the numerator or the denominator has the higher degree. So the higher degree here is the denominator, since this highest exponent is 2, and we do not have an exponent here. So we can use partial fraction or partial fraction decomposition to simplify this integral so that we can solve this. Because you cannot solve this using, you might try solving this using integration by parts, but you do not have a formula for this, no? So far. So one thing you should do, we should factor first the denominator. That's the first thing you should do. So this is factorable. You can factor the x. So this will now be equal to, I think I'll just write this down here. So you have the integral of 1 over x and then x minus 2. Okay? So in partial fraction decomposition, you can actually rewrite this into two, since you have two factors, you can decompose this into two terms. So you have the first term which has the x term as its denominator, and then for the second term you have x minus 2 as its denominator. That's it. And then you have to find the constant a and b, and then don't forget the dx. So the goal here is to find what is a and what is b, so that if you have this form, you can just solve this using substitution, which is just using ln, the ln integral, no? The involving the natural logarithm. Okay, so how do we solve that now? So we can have an equation here that equates these two things, or these two expressions. Okay, since these two are equal. And then what we should do here is multiply this by x, by this, no? By this, actually this is your LCD as well. So simplifying this will just cancel out. So we have 1 here, and then multiply this by this. So the x will cancel out, right? So this will cancel out. We have here a and then x minus 2, and then plus. So this will cancel out here. So we have only bx. Okay, that's it. So to solve for a and b, there are countless ways to do this. So actually, there are two methods to use. But let's start with the simpler one. I will discuss actually it is also simpler, but it is usually used for more complicated problems, which involves quadratic forms. Okay, so in here, the thing here is that we can assume a value of x. No? We can assume a value of x here so that we can cancel out a term. So let's say we substitute x is equal to 2. So if this is 2, then 2 minus 2 is equal to 0. We can cancel out this. Therefore, as you can see, you can solve for b. And then if you substitute 0 here, for example, then this will cancel out, right? So this will become 0 minus 2. So negative 2 times a. So you can solve for a, right? So let's do that. So to solve for a and b, you can assume, no? So you can let x is equal to something to cancel out a term to solve for the other variable. Okay, or actually the other coefficient. Although this is in somewhat way a variable, no, that we're trying to solve. So we let x is equal to 2. So if x is equal to 2, this will cancel out to 0. And then this will become 1 is equal to bx, or sorry, 1 is equal to b times 2. right? So therefore, your b here is equal to 1/2. Okay? So we already solved the b. So for letter A, what we can use to cancel out this b, so we can let x is equal to 0. So basically, we want this factor to be 0. Okay, so this is 0. So we have 1 is equal to a times 0 minus 2. So we have negative 2a is equal to 1. Therefore, a is equal to negative 1/2. Okay, so that's it. So basically, after doing that, you can go back to this again. So you have the integral of a over x. So this is negative 1/2 over x. And then plus we have positive 1/2 over x minus 2 and then dx. So we can integrate this separately. So what is the integral of this? So you can just factor out the negative 1/2. So this is negative 1/2 natural log of x, right? And then plus 1/2 ln of x minus 2. So actually you have to use substitution, but for this case, I think at this point we are already very familiar with how to solve for this one and also this one. So that will be the first example, the simplest example for integration using linear and distinct. No? So this example is actually case 1. Okay, so for next case here, so our next problem, how do we do this? So if this is already factored out, then this is a good news. No, we don't have to factor it. This denominator. So basically, again, if we have this form, then we can decompose this into the sum of these terms, no? So how many terms should we have here? So this is actually case 2, no? So this is a repetition with x minus 1. So we have to take into account x minus 1 and x minus 1 squared. Okay? And then for the third term, we have the third factor, which is x plus 3. So this will be just a, this will be b, and this will be c. And then dx. So basically, we want to solve for a, b, and c. So again, we can equate this to, this is equal to this. Okay? So x squared plus 9x plus 2 is equal to, over x minus 1 squared, x plus 3. This is equal to a over x minus 1 plus b over x minus 1 squared plus c over x plus 3. So the thing here is we can multiply this by the LCD here. This is actually also the LCD. We have x minus 1 squared, x plus 3. So simplifying this would just cancel out for this first term on the left hand side. So what remains here is this expression. And then for this first term, we can cancel out this a single x minus 1. So we have a and then x minus 1, x plus 3. For the second term, we can cancel out all of this, right? So this will be just x plus 3. And then for the last term, we have x minus 1 squared. Okay, so again, we want to solve for a, b, and c. So what we should do here is we can substitute either 1 to make this 0 or 3 to make this, negative 3 to make this 0. So let's, what should we do here? We can let x is equal to 1 to make this 0. So if this is 0, this is also 0 actually. So you have only these two terms. You can solve for letter b or this coefficient b. So you have, substitute this 1. So we have 1 squared and then plus 9, 1 squared plus 2 is equal to, so this will be just 0 and then is equal to b and then 1 plus 3 and then that's it. So we can solve for b. So b here, I'll just save you the time of solving this. B here is equal to 3. Okay. And then for the next one. So we already solved for b. Actually, you can all, if you, as soon as you solve the coefficient, you can actually substitute the value here already if you want. But what I will do here first is I will substitute first x is equal to negative 3. Okay. I will substitute the newly solved coefficients later. For later na lang, no? So if x is equal to negative 3, then we have negative 3 squared plus 9, and then negative 3 here, plus 2, and then equals 2. So if this is negative 3, we can cancel this out. We can also cancel this out. So we have c and then x minus 1, so negative 3 minus 1 and then squared. So I will just save you the time. The answer here should be, I don't have an answer actually pala, no? So let's solve this manually. So we have 9 minus 27 plus 2, and then over 16, right? So c here is equal to negative 18 plus 2, so negative 16. So this will be negative 1. Okay? So we already solved for letter B and letter C. What about letter A? The coefficient A. So we do not have any choices to make this 0, no? If that is the case, then what we can do is we can already substitute the B and C. So substituting the B and C here, we have x squared plus 9x plus 2 is equal to ax minus 1, x plus 3. And then you have, so b here is 3, so plus 3, x plus 3, and then negative 1, so negative x minus 1 squared. So how do we do this now, no? Well, actually, you can substitute any value of x. Any value except 1 and negative 3 to solve for a. So if you want 1 million, you can also do that. If you want 1 million, no? Or if you want negative 10, whatever you want. Even square root of 2, this will still be solved, no? So substituting here, a smaller number will decrease your calculation, no? So I'll just choose, either I choose 2 or I can choose 0. So for this case, I'll just choose 0 to make things easier, no? So we can cancel out these terms. So we have 0 squared plus 9 times 0 plus 2, and then equals 2. A, and then we have 0 minus 1. We have 0 plus 3, and then plus 3, and then 0 plus 3, then minus 0 minus 1 squared. So this will be equal to 2. We have here a, and then negative 1, 3, plus you have 3 times 3, and then minus 1. So negative 1 squared is 1, so minus 1. So therefore, solving for this, you have 2 minus 9, transposing this, and then negative 1, positive 1, and then all over negative 3 is equal to a. So therefore, a is equal to, you have negative 7 plus 1, so negative 8 over 3. Oh, where is it? I'm just checking my answer. Oh, so this is negative 7 plus 1. Also negative 6, sorry. So negative 6 over 3. So this should be negative. Let me just check. Negative 9. Huh? Oh, should it be 2? So let's just use a calculator. I'm getting confused. Sorry. So we have 2 minus 9 plus 1 over negative 3. So this is 2. Okay. So we use a calculator for just that. Okay, sorry. So the final answer should be, when we substitute this first. So substituting this, we have the integral of a. So we have 2 over x minus 1. and then plus b. So b here is 2. So we have 2 over x minus 1 squared. And then plus c. So c is negative 1. So this will become negative. And then x plus 3. And then don't forget the dx. Okay. So how do we integrate this? You just have 2 ln of x minus 1. How about this? Well, actually, you can rewrite this as 2 times x minus 1 raised to negative 2. So the integral here will be just, so plus 2, and then you have x minus 1 raised to negative 1 over negative 1. Okay? And then minus ln of x plus 3 plus c. So simplifying this, you have 2 ln x minus 1 minus 2, and then over, 2 over x minus 1 minus ln of x plus 3 plus c. So this will be your final answer. Okay, so that's fine. Let's move on to the next one. Okay, so we have this third example. So did we check before the exponents? Yeah, check the exponents now. So again, if you have a rational function, you have to check first if the denominator has a higher degree. So how do you check for degree? The highest here is x squared and x squared. And since they are multiplying to each other, if you simplify this, no, if you multiply this using FOIL method, this will become x to the fourth. Ano? So since this is higher than x squared, then the denominator is higher, then you should use the partial fraction decomposition. So we can write this one as actually you can factor this out further, no? So this is equal to x minus 1 and x plus 1. So don't forget to factor this out. But this one is not factorable anymore. No. This is not factorable anymore. So you should not, or you cannot factor this out. So this will be a quadratic factor. So if you have a quadratic factor, there's either case 3 or case 4. So since you do not have an exponent here, then this is just case 3. Okay, so we can write this again as we have x minus 1 and x plus 1. And then plus, you have x squared plus 4. So this one, you have a, you have b. But if you have this denominator as a quadratic function, this should be cx plus d, or constant times x plus a constant only. Okay, and then dx. So simplifying this, using this again, I'll just skip to the parts now. I'll just to save time, no. So this will become x squared plus 9. So equating this to this, and then simplifying, x squared is equal to 9. Sorry, x squared plus 9 is equal to a, and then we have x plus 1, and then x squared plus 4. Okay. And then you have here, I forgot to sorry. So for this one, for the next one, we have x plus 1. So we have b, so x minus 1 and x squared plus 4. And then for the last term, you have cx plus d. Cx plus d, you have, sorry, you have x minus 1 and x plus 1. Okay, so let's solve this first using the easiest method, no? So you can use x equal to 1 and x equal to negative 1. So let x equal to negative 1 first. So if this is negative 1, then you have negative 1 squared plus 9 is equal to, so this will cancel out. This will also cancel out. So you will, the term that will be left here will be b negative 1 minus 1, negative 1 squared plus 4, no? This one, okay? So simplifying this, I will save you the time. I already solved for this. So b is equal to negative 1. I hope I'm correct. Let me check. So this is equal to 10 over 2 times 5. Okay, that's good. We have, oh, oh, sorry, this is negative, right? So this is negative 1. So we have already an answer for B. So next one, you can use x equal to 1 so that you can cancel this out, right? So we have 1 squared plus 9 is equal to a, and then 1 plus 1, and then 1 squared plus 4. So a here is, okay, doing manual computations. So b here, a here is equal to positive 1. Okay. So what now? How do we solve for C and D? We cannot solve this anymore, no? Since there is no real value that will make this 0. So this will always be positive if you substitute any value or any real number in this x. If we square any real number, it will always be positive or 0. So this will not work anymore, the assumption method, no? So what can we do here anyways is we can expand. No? We can expand this equation, and then we can, what do you call this? We can, we can equate the left-hand side from the right-hand side. Let me just check what I did here. Oh, x is equal to 0 pala, no? We forgot the x is equal to 0. Sorry. Actually, you have one last pa pala. Sorry. So if we let x equal to 0, actually you have a solution here. If we let x equal to 0, okay, we can cancel this everything. So we already have a solution for a and b. So we can solve for d. Okay, I forgot the 0. So the thing here is you should substitute the a and b first. So let me just write this first. So we have a, so this is just x plus 1 and x squared plus 4, and then negative x minus 1 and x squared plus 4, and then plus cx plus d, and then x minus 1, x plus 1. So if you let x is equal to 0, then you can cancel this. So what remains here, the coefficient of the domain is just d. So 0, we have 9. So I will not write the x anymore, no? So 9 is equal to 1, and then this will be 4, minus, we have negative 1, we have 4, plus, so this is 0. So we have d, so d here, d, and then x minus 1, so 0 minus 1, 0 plus 1. So to solve for d, so d here is equal to, we have 9 minus 4. Actually, this is 9 plus 4. Okay, minus 4 na nga. Minus 4 again, and then over negative 1, right? So d here is equal to, so negative, positive 1 over negative 1. So this is negative 1. Just checking if this is correct. Okay, correct. Okay, so we have a value already for d as well, so a, b, and d. So for the last one, if you have only one coefficient remaining, you can just substitute this d here, and then you can substitute any value of x, except, of course, 0, 1, and negative 1. So I will just write things down here. So you have x squared plus 9 is equal to x plus 1, x squared, I don't think it will fill, sorry. Let's just use another slide. So x squared plus 9 is equal to, you have x plus 1, x squared plus 4, minus x minus 1, x squared plus 4. And then you have cx plus d. Cx plus d. So d here is negative 1, so we have minus 1. And then, and then, what's next? Sorry. Where is it? Wait, what? Okay. Sorry. X minus 1 and x plus 1. So you can assume any value of x at this point if you have only one last remaining coefficient. So you can try 1 million or whatever. But I will just use here the smallest number available. I will just use 2. So this will be 2 squared. Oh, 2 squared plus 9 is equal to. So I will just solve this one. This is 3. So 2 squared plus 4, this is 8. And then minus, so 2 minus 1, so 1. 2 squared plus 4, so 8. Plus you have here 2x minus 1. And then you have 1, you have 3. Okay, simplifying this. So you have here the left hand side, you have 13. Transpose this to the other side, so 3 times 8, so negative 24. And then plus 8. And then divide this by 3 is equal to 2x minus 1. So 2x minus 1, this will be plus 1 is equal to 2x. And then divide this by 2 over 2. Oh, sorry, why is this 2? It should be C, sorry. So this should be C, and x here is 2. So 2C dapat pala, ano? So 2C, so this will be just C. So therefore C should be equal to, do we have here? So this is 13 minus, so 13 minus 16. And then over 3. So this is negative 3 over 3. So this is negative 1. So plus 1 over 2. So this is just 0. So 0 over 2. C is equal to 0. Okay? So that's it. Now you will just substitute the values here. So if you integrate this original problem, okay, you just have to substitute the values here. And then you can now integrate. So this is equal to the integral of a. So a here is 1. So you have 1 over x minus 1. And then plus b. So b is actually negative 1, right? So negative 1 over x plus 1. And then plus cx plus d. So since we do not have a c, so 0 plus d. So d is negative 1. So this will be just negative 1 over what do we have here? X squared plus 4. Okay. And then integrate. So this will be ln of x minus 1 minus ln of x plus 1. And then you have here, this is actually arctangent, no? So arctangent, we forgot this should be 1/2 arctangent x over 2. So remember this, if you have the integral of 1 over u squared plus a squared, this should be 1 over a arctan u over a. So your a here is equal to 2, your u here is equal to x. So this should be your answer. Now, we can solve this already, or this is already your final answer, but you can actually further simplify this. So using the property of logarithmic functions, you can combine these two into ln of x minus 1 over x plus 1. And then you have negative 1/2 arctan x over 2. If you want to simplify this, this will be also another alternative form of our final answer. Okay, so that's it for this example. Let's move on to another one. So integration of rational functions. So using partial fractions, how do we solve for this now? Okay, so again, if you have the denominator as a higher degree, as your higher degree than the numerator, then you should use partial fraction. Now you have here a quadratic factor that cannot be further factorized. So it will retain its form, and we can simplify this into we have a over x plus you have bx plus c over x squared plus 2. And then since this is repeated, you have to also take into account x squared plus 2 squared and then dx plus e. So it looks like it is a short one, but this is actually a long computation, a long integration using partial fractions. Now, uh, if we rewrite this one again, so we have here 8 is equal to a times x squared plus 2 squared, and then plus we have plus here. Actually, you can use also imaginary numbers if you want. You can let x as an imaginary number, but we're not yet there, you know. Okay, let's simplify this. We have bx plus c, and then we have x squared plus 2, and then we have bx plus e, and then this is just x. Okay, so the simplest one here that we can solve already is when x is equal to, actually I forgot the x here. I'll just make this x cubed plus 2x. So why is that? Because we'll only cancel 1 here. If you multiply this by bx plus c over x squared plus 2, you have x here. So what will remain is x, x times x squared plus 2, that will be x cubed plus 2x. So again, okay. So if you let here x is equal to 0, you can actually solve for a. So this will become 0. So 0 plus 0, 0. So cancel these two terms. You have 8 is equal to a 0 plus 2 squared. So therefore, a is equal to 2, right? Let's check. Where are we? Okay, a is equal to 2. So that is only that is the only coefficient that we can solve. So after that, okay, how do we do this now? We can let x is equal to 0 pala. Hindi, not anymore. We cannot do this anymore, no? So if that happens, what we can do here is actually we can expand this. So we can simplify this, simplify, simplify. So this will be a long one. So we have, and also you can substitute that 2 here. I will substitute this already here. So you have 2 times, so expand this one, you have x to the 4th plus 4x squared plus 4. I hope that's fine. Okay. And then plus we have by a FOIL method, you have bx to the 4th 2bx squared inner and last plus 2cx. Okay. And then for this one, you have plus dx squared plus ex. So at this one as well, no, you can simplify this. So I will just simplify this to make things faster. So this will be 2, this will be 8, this will be also 8. So that's it. What we should do here for the next step here is we should group everything based on its degree. So you have 8, or basically you just combine the like terms. So you have 2 x to the 4th and bx to the 4th. And then cube, for the cube, we only have one term for the cube, right? Sorry, I'm just checking my notes to make things faster. So that I won't commit any mistakes anymore, no? So you have cx cube for the second term, the cube ones. And then for the quadratics, or the second degree, you have plus 8x squared, and then plus 2bx squared plus dx squared. So for the x only, you have plus 2cx plus ex. And then for the constant, you have 8. So what I will do here is I will factor out this x to the 4th. So you have 2 plus b x to the 4th. And then since this is so low, we have just cx cubed. And then factor out also the x squared here. So you have 8 plus 2b plus the x squared. And then plus you have 2c plus e and then x plus 8. Ayan. Okay? So what you should do here is you can equate everything here. You can equate everything here to the left-hand side. So basically, what does that mean? So whatever is your left-hand side, which is usually polynomial, a polynomial, is let's say you have here 3x to the fourth. So what you should do here is you will equate the coefficient versus this coefficient. So basically, since we do not have an x to the fourth here on the left-hand side, this will be just 0. So you have here 0x to the fourth, and then 0x cubed plus 0x squared plus 0x plus 8. So basically, what we are doing here is equating the coefficients. That is the technique. No? So 0 is equal to, I'll just write this down here, this space. So 0 is equal to 2 plus b, okay? And then 0 is equal to c, okay? Equating this to the left-hand side and right-hand side. And then you have 0 is equal to 8 plus 2b plus d. And then you have 0. So where is this coming from, no? So you have 0 is equal to this 0, and then 8 is equal to this 8. So 0 is equal to 2c plus e, and then 8 is equal to 8, basically. So we already have this as our answer. So we can just do this, no? So we already have an answer for c. So c is equal to 0. Okay, we have an answer for c. For b, so b here is equal to negative 2. So we have an answer for negative. So for b, we have a negative 2. If you know c is equal to 0. So if c is equal to 0, you have 0 is equal to e. So e is equal to 0 as well. So, and the last one, so we know that b here is equal to negative 2. So you have 8 times minus 4 plus d is equal to 0. So d here is negative 4. So d here is negative 4. Yeah. So therefore, we can solve this already. No? So yeah, let me just create another slide for now. So a here is equal to, like a, where's the a? Where is the okay, a is, we already solved the a. So you have the integral of 2 over x. And then b here is negative 2. So plus negative 2x. So we do not have a c, so this will be just negative 2x over x squared plus 2. And then dx plus b. So d is negative 4, a is 0. So negative 4x over x squared plus 2. And then to the fourth power. Sorry. Second power lang pala. And then dx. So can we integrate this? Actually, we can, no? So for this one, we can integrate. You might get confused here and here. So let's just use substitution, no? So u is equal to x squared plus 2. So du is equal to 2x dx. Yeah. So this will become integratable, as you can see. Let me just separate this pala, no? So the integral of 2 over x dx, and this should be 1/2 dx over x. And then we have here minus the integral of 2x dx over x squared plus 2. And then minus, so in here you have, again, u is equal to x squared plus 2. Okay, yeah. So I'll just factor out 1, 2. And then the integral of 2x dx and then x squared plus 2. So what happened here? So a technique I did was I just factored out this negative 4x to negative 2 times 2x so that we can directly substitute this to our problem, similar with this. Okay? So this will now be ln x. Actually, the answer here, I'll just skip to the answer now. So this will be just ln of u, which is x squared. Let's check the answer, sorry. To make things quicker, negative ln x squared plus 2, and then plus, okay, plus 2, and then this will be 2 over x squared plus 2. So, yeah. So this will be your final answer. Okay, that is a lot. Um, okay, so I hope there is no questions here. But again, if you have any questions, you can raise them during class. Okay, so we are done with integration by partial fraction. There are a lot of things to remember there. I just want to add this since we have problems in the book or the textbook that is similar to this. So if the numerator, as you can see here, is higher degree, or actually or equal to denominator, then you should use long division. So how do we do this now? So for long division, basically you're trying to divide x cubed plus x by x minus 1. So how do you do this? There is a long method. Okay? There is a long method to simplify this, no? And for me, the shortest way is always the best because you do not have to memorize or write a lot of things. So if you have x cubed plus x here, so take note of what I'm going to do here. So you have 1, 0, 1, and 0. So where did this came from? So the numerator here is 1x cubed, diba? So the coefficient is 1. And then since we do not have an x squared here, this is 0. And then x here, the coefficient of x is 1. And then since we do not have a constant, or actually x raised to 0, or the constant, so there this will be 0. Now, I will put here, so the format for dividing polynomials is x minus r. So r should be positive here. So therefore, if this is negative 1 or x minus 1, this should be positive 1. So remember that as well. Okay, so what's next? So the next part here, the simplest part, is we just have to bring this down. The first operation is just bring down the first one, this one. And then the next step is to multiply this by 1. So this will be 1 times 1, so 1. And then after that, add this 2. So add, so we have 0 plus 1, 1. Excuse me. Sorry. So do this again, multiply this 1 by another 1. So this will be just another 1. And then you have 2 here. So 1 plus 1 is 2. And then multiply this again. So you have 2 here. And then after that, 0 plus 2 is 2. Then what's next? So the next thing here is that this is actually the coefficient of your x squared. So if this is x cubed, this will now be x squared. This will be x. This will be x raised to 0. And this is your remainder. So how do we write this down? So if we divide x cubed plus x over x minus 1, okay, this is actually equal to x squared plus x plus 2 plus 2 over, so since this is a remainder now, 2 over x minus 1. Okay? So at this form, so as you can see, you can integrate this, you can integrate this, you can integrate this, and so on. You can integrate this. We can now solve the integral. So the integral will now be x squared plus x plus 2 plus 2 over x minus 1, and then dx, and then simplify. So you have x cubed over 3 plus x squared over 2 plus 2x, and then plus 2 ln of x minus 1 plus c. Don't forget the c. Okay, so that's it. This is your final answer. Okay. Okay, the very last problem at last, finally. So when an integrand contains an expression to form square root of or the nth root of g of x, then the substitution u is equal to n g of x may be effective. So strong word here, no? So may be effective. So there is an element of trial and error. If nothing works really, basically, then you might try doing this substitution. So if you have this, you might think of using integration by parts. Actually, this might be solvable using integration by parts. Might be. But let's try an alternative way. So again, this substitute, sorry, this this new concept introduces us to use rationalizing substitutions. So we should let u is equal to the square root of x plus 4. Okay? And then finding the derivative of this. So we have du and then equals to 1 over 2 what? Wait. Sorry. Ah, what? Wait, wait. Ah, sorry. So this if we integrate this, sorry, if we differentiate this, oh, what? Hmm. Oh, I forgot about this. So what you can do here is this is also the same as when you do if you square both sides, so you have u squared is equal to x plus 4, right? So if you find the derivative of this, you have 2u du is equal to dx. So using this, you can change this one, and you can also change this one. So for changing this one, you can also rewrite this as x is equal to u squared minus 4. Yeah. Okay. So you have to use this 3 substitution, no, to solve for this. So you have u, and then you have here u squared minus 4, and then dx is 2u du. Okay. So simplifying this, you factor out the 2, you have u squared over u squared minus 4 du. Okay. So if this is the case, what should you do here? You can use rationalizing substitution, right? Sorry, long division or synthetic method, or synthetic division. So for this, but I will teach you a technique. No? There is actually a technique here that will make things easier, even easier. So if you have this case, what you can do here, so we want to cancel out u squared minus 4. So basically, what I can do is I can add negative 4 here and add a positive 4 here. So what happens here now? If you simplify this negative 4 and 4, this will be just equal to 0. So basically, nothing happened. So we can expand this into this form. So why is that? So that you have u squared minus 4 over u squared minus 4 plus 4, right? So you can just simplify this and also simplify this as two separate simpler fractions. And then you have 4 over u squared minus 4. It will save you time before doing the synthetic division. So this will cancel out into 1. So therefore, we can integrate this already. So this will be just, actually not yet, no? We have to use partial fraction. So minus 4, and then u squared minus 4, and then du. So this one is integratable already, but this one is not. So you have to use integration by parts here. Sorry, integration by partial fraction. Okay. So, okay. So let me just integrate this first, no? So integrating this will be, I think this will be easier. So integrating this, you have u. So factoring this, you have u plus 2 and u minus 1. U minus, so u minus 2 and u plus 2 is equal to, so you have here a over u plus 2, and then b over u minus 2, and then du. So the u here, solving for this, again, simplifying this, now equating this to this, it will yield this 4 is equal to a, and then u minus 2, and then plus b, and then u plus 2. Okay, so if u is equal to 2, we'll just save the time, no? So you have b is equal to 1, right? B is equal to 1. Yes. And then if u is equal to negative 2, what happens is this will cancel out. So negative 2, so negative 4, so a is negative 1. So therefore, the integral of this is equal to, so the integral of this is equal to negative 1, this is positive 1. So the integral of 4 over u squared minus 1, minus 4, sorry, is equal to negative ln of x, or sorry, u plus 2, and then plus ln of u minus 2. Or you can simplify this even, no, to ln of u minus 2 over u plus 2, knowing the properties of logarithmic functions, plus c. So therefore, for solving this, so let's go back to this again. So the answer here will be 2 times you have u, and then minus ln u minus 2 over u plus 2. Okay. Huh? What happened? Okay, let me just check this later now. Okay, this is correct. I think this is correct. Plus c. So you have to change the variables again from u to what? So u is equal to the square root of x plus 4. So creating another slide. So this is equal to 2 times the square root of, so I'll just distribute this as well, no? Correction to term. So 2 times square root of x plus 4 minus 2 ln of the square root of x plus 4 minus 2 over square root of x plus 4 plus 2. Yeah, plus c. So this will be your final answer. Okay, so that's it. So I hope you learned something with this lecture. See you guys again during our meeting. So see you guys again very, very soon. Bye guys.